Hey, Mark Thrimm and Marcus House with you here, and welcome to our collaborative series of the SpaceX Mars colonization mission, shown here with the newly presented Interplanetary Transport System rocket. Now, before I say anything here, Mark Thrimm has spent a massive amount of time meticulously creating this SpaceX ITS mod, which is now a very close approximation to the presented SpaceX design. He has literally been pouring his spare time into these custom modded parts over the last few weeks, and already has the mod up for all you guys to play with. The link for this mod is in the description, of course, and it supports both Kerbal Space Program 1.2 as well as 1.1.3. In this video, Mark is in the pilot seat at the controls piloting the SpaceX ITS, while I'm going to pretend to be entertaining and discuss some of the finer points of the mission and the amazing ship design that is the SpaceX ITS. So for those of you who are not overly familiar with the SpaceX ITS design, we have a link for this in the description as it's well worth a watch. This is the official video from SpaceX. The rocket is simply massive. There is really no way of comprehending its size and power. The largest rocket launched to date, of course, was the Saturn V, which took men to the moon. And this massive beast had a first stage that ferociously consumed around 13 metric tons of fuel every second, powered by 5 Rocketdyne F1 engines. The entire Saturn V fully loaded with fuel was close to 3,000 tons in weight. Now, that's mind-boggling. Let's compare this though to the SpaceX ITS design. The SpaceX design is proposed to weigh up to 10,500 tons, which is around 3.5 times the weight of the Saturn V. It's also supposed to have 42 Raptor engines in the first booster stage, and these will be fueled with liquid methane and liquid oxygen, punching out a combined total thrust that is just over 3.5 times that of the Saturn V as well. So these Raptor engines themselves will have an unprecedented amount of thrust, and small prototypes of this engine have already been measured to have 3 times the chamber pressure to that currently used by the existing SpaceX Falcon 9 Merlin engines. So being anywhere near 42 of these monsters all firing together to boost this massive ITS vessel off the ground would, I suspect, make anyone lose all control of their various orifices, so I suspect there would have to be quite a distance required for spectators to prevent such messiness. As we head up above 2,000 meters per second, the booster will decouple and the ship stage will fire its engines to head up to a low Earth parking orbit. For the ship stage, there will be 6 vacuum Raptor engines, which are optimised for, obviously, flight out of the atmosphere, and there are 3 Raptor sea level engines in the centre to initially assist in getting the second stage some of the way to orbital velocity, and as well, of course, to use when landing on the surface of Mars within the thin atmosphere. So while stage 2 is powering up to a parking orbit, the booster can flip 180 degrees to point back towards the launch pad. As soon as the RCS thrusters have it facing the opposite direction, the centre cluster of 7 engines, along with the inner ring of 14 engines, will thrust the booster backwards, not only cancelling out its entire horizontal velocity, but also shooting the booster back towards the launch pad in order to land in the actual launch mount itself. I imagine also if you fired the outer ring of 21 engines at the same time would give the almost empty booster at this stage a thrust to weight ratio that would be so high it would probably damage the booster due to such massive G-forces. As it is, the G-force would be heading up there towards 20 G using the central set of 21 engines anyway. After the initial boost back burn, the booster will flip again, ready to do its final deceleration burn as it comes back down to land. It's then only going to fire the central cluster of 7 engines to wipe off this final velocity. These 7 engines are the only engines which will actually have a gimbal on it, and this basically meaning, of course, that the engines can dynamically tilt a few degrees in various directions to allow better pitch and yaw control of the booster when descending into land, and as well, of course, to provide better control in its original ascent and boost back burns. Speaking of landing, the SpaceX presentation shows the booster incredibly landing on the launch mount itself, which I think you'll all agree is a freaking amazing proposal, and I know we'd all love to see this one day. That being said, there is no way Mark here can land with the precision of a supercomputer. With any luck, we'll be touching down close to the launch pad. Let's see how we go. And... flawless. Nice work, Mark. Flawless landing. So as the booster there touches down, it will start preparing to launch a second tanker refueler to send up after the ship, but we'll cover that later. For now, the ship is going to be very close to full orbital velocity at around the same time the booster lands, and when the ship stops firing its engines finally, it's essentially going to patiently circle the globe in a low Earth parking orbit until the tanker arrives to refuel it quite soon after. And finally deploying those massive solar arrays to generate a huge amount of power for use by our elite Mars crew on their maiden voyage. If you haven't already viewed part 1 of this video, check it out here first. In part 1 hosted on Mark Thrimm's channel, we covered the preliminary ship and booster segment of our mission heading to a parking orbit, so check that out. In part 2, we are looking at the tanker refueling section of the initial mission to Mars. Now, before I say anything else here, and as I said in part 1, Mark Thrimm has spent a massive amount of time creating this SpaceX mod for us to use while making this series, and this is very close now to the Interplanetary Transport System design presented by Elon Musk just a few short weeks ago. The link for this mod I do of course have down in the description if you do want to have a play with the vessel, so enjoy that. In this video, Mark Thrimm is in the pilot seat at the controls flying the vessel, while I'm going to try my best to explain the awesome concept of the ITS design throughout this segment of our mission. If anyone isn't familiar with SpaceX's ITS design, there is a link to the original presentational video down in the description, so do check that out, it is just awesome. So in part 1 we launched the ship and landed the booster, and of course as suggested by the official presentation, the booster will refuel back at the launch mount while the tanker stage is added to the top of the freshly landed booster. Of course the ship from part 1 is awaiting the tanker in a low Earth parking orbit, so there is no time to mess around. The tanker needs to launch quickly to meet up with the ship and refuel it so it can then head off to Mars. So there is a very good reason why the tanker stage is needed to do this refueling step, and although the entire process is a little more complex than the mission to the moon many years ago, there is a very good reason why this refueling method is a terrific idea. Firstly, if the ship and booster were to launch and head to Mars from a single launch without refueling in orbit, it would require a 3-stage vehicle at an estimated 5 to 10 times the size and cost. Now, as specified in the presentation material, by spreading the lift capacity across multiple launches, it substantially reduces development costs and lessens the time needed to develop a much larger disposable rocket. Not to mention, of course, that SpaceX is all about reusability, and if you've seen any of the recent Falcon 9 drone ship landings, then you'll know why there is so much excitement around this reusability concept to essentially reduce the cost of space travel by a very large percentage. So, although there are performance losses due to the reusability of the boosters, it is well worth the cost. As said many times by SpaceX, reusability is the key to making human life multi-planetary, and this is the real inspiring end goal, and it will allow humans to transport much more cargo to Mars in a much shorter time frame. The tanker itself will be heavier than the ship component simply because it will be almost fully loaded with fuel. Although we can't find a source for this, we very much expect that the tanker's booster stage will reach a slightly lower velocity than the ship stage did before the booster's main engines cut off. This is simply because the tanker itself is proposed to weigh quite a bit more, as it's going to be almost fully loaded with fuel. The ship of course will have a lot more empty space for the 100 passengers that are hopefully not going to be packed too tightly into the ship for the long journey to Mars. After the tanker intercepts with the ship, the two vessels will then dock together and the tanker will refuel the ship, leaving just enough fuel to return to Earth again fully reusable. The ship itself will have heat shielding on the bottom face of the tanker and ship, allowing it to re-enter Earth's atmosphere, similar to the retired space shuttle. All the same though, like any re-entry, it could very well mean a brown trousers time for those awaiting a signal to indicate the tanker made it through the re-entry without burning up. It is imperative, of course, that the tanker remains tilted and facing the correct angle to ensure the heat shielding is in the correct placement. Any deviation can cause disaster for the tanker, and as we recently read in SpaceX's subreddit, Elon announced that both the spaceship and the tanker would have split body flaps for pitch and yaw control as well. So as the tanker descends into the lower atmosphere, it will then flip over using these controls and come in tail first. The sea level engines then will wipe off the remaining velocity and then come down to land using 3 massive landing legs. So now, of course, our ship in orbit, fueled and ready for its journey, can head off to Mars using only the 6 vacuum engines. This Mars colonization mission will take a select number of very courageous humans on the longest and most dangerous exploration mission in evolutionary history. If you haven't already viewed earlier parts, check them out here. In part 2, we launched the tanker, refueled the ship, and then re-landed the booster. The ship, of course, is now completing its Mars transfer burn and ejecting from Earth much faster than most launches would be done previously. The main goal is to get passengers to Mars in the lowest time possible. The average transfer time to Mars with the ship will depend on the position of Mars in its orbits. Mars does actually have a slightly elliptical orbit around the Sun, meaning that it does vary quite a bit in its distance from the Sun. In the SpaceX documentation, it is estimated that the average transfer time will be around 115 days, so just a little under 4 months. A regular bare minimum Hohmann transfer of around 3.6 kilometers per second to Mars would generally take over double this time, so the ship needs to eject from Earth at a much higher velocity than normal to essentially cut the trip in half like this. Again, this is all possible due to the extra delta V the ship can obtain by refueling in orbit. So instead of a 3.6 kilometer per second ejection burn, SpaceX's ship would need to eject at over 5 kilometers per second. With the solar panels deployed after the transfer burn, the ship is spec'd to obtain 200 kilowatts of power. As there is no day-night cycle after leaving Earth's sphere of influence, the solar power will be constantly obtained, so onboard batteries should stay fairly constantly charged throughout the entire journey. Obviously though, the amount of solar energy hitting the panels will decrease depending on the distance from the Sun. So if the panels are to receive the full 200 kilowatts of power just after ejecting from Earth's sphere of influence, when closer to Mars the panels would, we imagine, get roughly 50% of this value, and less again of course when landed on Mars itself. Mars of course has a day-night cycle very similar to the Earth, spinning once every 24 hours, 37 minutes and 22 seconds. So similar to Earth, batteries will need to be fully charged through the day and power conserved as much as possible during the night. The SpaceX presentation video mentioned an interplanetary coast speed of just over 100,000 kilometers per hour. This would of course be the velocity of the ship while in its solar orbit, but the more impressive figure here is the Mars entry velocity of 8,500 meters per second. So this is the intercept velocity that the ship will be travelling at when it's actually reaching Mars. From interplanetary space, the ship will enter the atmosphere either capturing into orbit or, as mentioned in the SpaceX presentational documentation, proceeding directly to landing. Now, we've tried this a number of times and we suspect it is more likely that the ship will probably aerobrake in 2 passes. The first aerobrake to get into a Mars orbit, and then the second to aerobrake and land. We say this simply because of the very fast Earth to Mars transfer. It seems a little unlikely that the aerobrake could be done in 1 pass, but then again, there is a lot of surface area on the ship to help slow it down, so who knows. It has been stated that by using the ship's aerodynamic lift capability and advanced heat shield underside, the ship would be able to decelerate from entry velocities in excess of 8.5 kilometers per second at Mars, with an approximate 4 to 6 Gs of deceleration. The escape velocity of Mars is around 5 kilometers per second, so at a bare minimum, around 3.5 kilometers per second of the ship's velocity will need to be wiped off in order to get captured. The benefit of first getting into a Mars orbit is that then there is more time to analyse and plan the final aerobraking manoeuvre and more accurately predict landing locations. The heat shielding itself is proposed to be the same material as used on the existing Dragon spacecraft, or at least an evolution of the Pika material. SpaceX claim it to be the most advanced heat shield ever flown and can potentially be used hundreds of times with only minor degradation each flight. For anyone interested in the Pika material, there is a link to a related video in the description. The long-term goal is to load the ship with 100 passengers at a time, but this will almost certainly not be the initial crew number. In fact, the first crew may only have enough human capability to start setting up the basics and begin testing life on Mars, perhaps only 10 or so. This will obviously be an extremely precarious mission, and like any dangerous exploration mission, the chances of death are going to be high. That being said though, just imagine being the first life form in the history of the Earth to step onto another planet. I mean, there can't be a much better way to go, can there? On this first mission, there would be no way to refuel and return to Earth in the short term, and one of the primary critical tasks for the first humans would be to set up an initial small propellant plant to begin refueling the ship for a future mission. This would then be expanded over time, but it would utilise the easily obtainable carbon dioxide from the atmosphere and water ice from the surface of Mars to generate liquid methane and liquid oxygen to refuel the ship. The ship, of course, could then be sent back to Earth to refill with new crew and cargo to return in the very next available transfer window to Mars. If you haven't already viewed earlier parts, check them out here. In part 3 we landed the Interplanetary Transport ship on the surface of Mars for the first time, but now it's time to start the difficult task of setting up the very first Martian colony in order to actually survive on the red planet. Let's make the assumption that only 10 humans will make up the first Mars mission, and actually let's also assume that we have 5 years to set up a base that can be fully self-sustaining, well, without additional food sent from Earth, that is. Now, because the ITS will be designed to transport 100 people with required cargo, for this mission all the remaining space that would normally be taken up by the other 90 people can be used instead for more cargo, a lot more in fact. Astronauts on the International Space Station currently consume around 3.8 pounds or 1.7 kilograms of food per day, so just over 3 tons of food per person will be required for the 5-year trip. So 30 tons of food for the entire crew of 10 astronauts should keep them well fed and happy for 5 years, well, hopefully happy. Water, of course, is largely recyclable, and additional water can also be obtained quite easily from the Martian surface, so a few tons of water should be more than enough for the entire crew. Now, the SpaceX documentation suggests that the ITS is capable of delivering 450 tons of cargo to Mars, so let's overestimate our food and water needs for the 5 years and make the assumption that we have around 400 tons of cargo space allocated for equipment and cargo. The primary mission for our first 10 astronauts will be to establish a small propellant plant on the Martian surface. These brave human settlers will need to be very good at digging beneath the surface and hauling up buried ice, which will then provide the water needed to make the liquid methane and liquid oxygen propellant. The fuel will then be stored, and this would allow future ships to be refueled and returned to Earth. At the same time, mining operations could double as a construction job, allowing the hollowed out mined space to be utilised as a habitation or storage area. There are many wonderful 3D printed habitat concepts being presented lately, and NASA in particular is offering a substantial cash prize with their 3D printed habitat challenge. This prize challenges inventors to create new ways to build habitat modules where future space explorers can live and work. The competition asks inventors to use readily available and recyclable materials to 3D print these habitat segments, so who knows what 3D printing machine may be possible in the near future. As the mining facility gets underway, in parallel a series of transparent domes could be erected outside to serve as greenhouses. This would allow the first plants to be grown with step one of this process perhaps being to experiment with algae farms. There have been several proposals actually suggesting that algae could essentially produce nutrient-rich food quite rapidly. There could then be trial vegetables growing alongside, such as potatoes and peas and that sort of thing. Tests done so far in similar soil types found on Earth to that found on Mars does seem to indicate that quite a few plants should grow well in the Martian soil. Even more interesting are proposals experimenting with insect farms, which could provide an efficient source of protein, which will also, at the same time, consume and process many different kinds of bio-waste as raw material. I mean, who wouldn't want excrement-fed insects to form part of their balanced diet? I mean, it seems like a no-brainer to us. In the long term, being able to send many thousands of people in many ships simultaneously is the goal here. The success or failure of the first few human exploration missions, though, will determine how fast we can build the infrastructure needed to ferry settlers to Mars from Earth. 2 years after our ship launched to establish the first base on Mars, the propellant plant is now operational, the ship has slowly been refueled, and the ship is now ready to launch. This refueled ship can launch a huge volume of samples and experiments back to Earth, and escaping gravity on Mars is of course much easier than Earth due to the lower orbital velocity required to reach a stable orbit, as well as of course the very thin atmosphere on Mars. This all makes for a much more efficient launch, also quite free from the heavy atmospheric drag that we face here on Earth. Of course, the very first ship may perhaps stay on Mars and form a more permanent part of the first base of operations. It could even be left here as an historic landmark, as an example. It would depend largely, we imagine, on the status of the first base and how the colonists have gone creating the space they need to be comfortable until the next ship launches to Mars. Speaking of which, while our ship here is heading back to Earth, a new ship has been constructed and launched to make its first journey to Mars. This ship, which we'll imaginatively call Ship 2, is now loaded with 50 new astronauts skilled in a variety of fields. Scientists, botanists, engineers, builders, and many other skill sets will provide a huge set of combined experience for the growing colony on Mars. Of course, along with this new crew, a new motherload of cargo will be coming with them to Mars to join our already established colony. In another short few months, our little Mars colony will have grown to accommodate 5 times the number of abled bodies. Along with the new added settlers, new equipment unloaded from the cargo bay will have been redesigned based on the hugely valuable data obtained from the first 10 Martians already inhabiting the colony. As Ship 2 heads to Mars, Ship 1, finally after its long journey back from the Red Planet, reaches Earth's atmosphere where it can aerobrake in a controlled manner until the velocity has been reduced enough to fully come into land. Ship 1 will touch down with the very first samples from Mars ever returned to Earth, ready to be refurbished for its next exciting mission, perched up, of course, on one of the many boosters that have now been manufactured to send the growing number of ships to Mars, perhaps even to other exciting locations in our solar system.